So you probably have seen this image, and this is our STM study on the kind of quantum dot our collaborators grow for us. So this is the large quantum dot, and this is the smaller quantum dot. And usually when we look at our study, we look at the quantum dot that are this small, and they are not really so-called a spherical object. They are more like a pancake, okay? So laterally, they are between 10, 20 nanometer, and in thickness, 4 to 5 nanometer, and that's a quantum dot. And so, and then if I only think about a state within the quantum dot, okay? If I only think about a state within the quantum dot, then I'm really, I can, and I also only talk about the excitonic state. I want to define some terminology. First, if I don't excite any electron in the hole, I will call that no exciton state, right? Then I'm going to call that vacuum state. Okay, sometimes I use 0 for vacuum, sometimes I use 0 for exciton ground state. But just remember, vacuum state is also what we define as one kind of state. And then one exciton ground state, that is when electrons go to the ground state of the conduction band and the hole go to the ground state of the valence band. And that is the lowest state for exciton. And then anything higher than that, I would just call that one exciton excited state. And how do we observe such an exciton state? So there are many different ways. You can excite it a lot of hole and electron and just let them drop down there. And then at some point at this state, you're going to have, you create this situation, and then you just look at the emission. Then you will know what this transition is, because the energy, it would be this, the difference between the two. But of course, this is a single particle picture. You still need to do the many-body correction, the Coulomb correction. So then, but let me just use this energy diagram to present. This would be the exciton ground state. Then you can excite it to the continuum, or you can make an excitation between these two. And that, once you create that, then before it radiatively relax over here, it will drop to this state and then emit the light coming out. Okay, and that is what we usually call photoluminescence excitation. Okay. And for many years, if we really talk about near resonant excitation, we always talk about this, right? But then this is the true resonant excitation, okay? Is you can excite, use a laser to make a transition between this state and that state. Then look at the light emitted out at the same energy. This was considered impossible for many years until a few years ago. So for many years, this is what people usually do. For, I would say, half of the presentation, I will talk about what has been achieved using that technique. Okay. Ooh. So, but first, you know that exciton, all those quantum dots, say the whole field in a long time ago, what they are suffering is the quantum dot, they are reasonably close. How would I be able to find out that I'm only probe individual quantum dot? Right? The quantum dot distance is 50 nanometer, 100 nanometer, way, way smaller than the diffraction limit. And so they have been, so in the last time lecture, I told you the first one who got this was Harold Hess at the Bell Lab in 1996 or 1994, I forgot. Anyway, they are the first one who used a near-field optical microscope to see individual quantum unit. But then it was in 1996, I think Dane Gammon at the NRL tried to use this narrow aperture technique, and using the narrow aperture technique allowed them to investigate individual quantum dot. And then we came out with a different technique, and we ended up to be able to allow us to map out the distribution. We don't even need to create an aperture. We can already see where individual quantum dots are. And the trick behind it is to rely on the laser line is rather reasonably sharp. If I say I have a laser line that is 100 picosecond. No, it's 100 micro eV in width. Then the quantum dot usually about 30, 40 MeV. Okay, so when I come here in this area, say 20 micron by 20 micron, I think it has about, let's see, for 100 nanometer by 100 nanometer, we have on the average about 4 quantum dots. So for 1 micron by 1 micron, we have on the average about 400 quantum dots. So for 20 micron by 20 micron, then we have on the average about, let's see, 160,000 quantum dots, I think, right? 400 times 400, that's 160,000 quantum dots. Then that is typically our illumination area. Then at 160,000 quantum dots, how can I know that I only look at just a few? Well, the key is, in this 160,000 quantum dots, when I use a laser line to come here and shine and hit on it, because not all of them have the same excited state. Not only that, not all of them have the same ground state either. So if I come up here, then I can only excite maybe one out of, say, maybe 400, okay? So I already, for laser light shine on this about 20 micron by 20 micron area, I only excite about 400 quantum dots. And this 400 quantum dots, they have their emission energy spread over about 30 MeV range. Then each one of them will also emit a different energy. And they are emitted, so about this 20 micron by 20 micron, they emit energy, a different energy, and then most of them I can spectroscopically identify individual of them. Not only that, I can also then spatially map them out using what I described earlier. Let me see, I think I'm going to, So this is the movie that I do. So what I want you to know that is, this is the map that we have on the spectrometer. We have this represent a spatial location along one dimension, and this represent the emission energy. Then what I do is I'm going to start scanning the laser energy. So when this thing matched, when it show bright that is at this particular laser energy, I have this quantum dot emitting. It is at this spatial location along one dimension, and then it emits at this energy, and I know its excitation is at the other energy. So I would continue by skipping that slide. So that slide is basically show you we can then ended up image the spatial location of individual quantum dot. We will know what is ground state energy. We will also know its excited state energy. And then by using that, we can then map it out, and then all different kind of energy structure. One thing that we have noticed, that is, this is the emission energy. Then we start exciting the excited energy. So for one particular quantum dot, I know this is what this would be its excited state energy relative to this emission energy, and then I will map out its excited state structure. And you will find out, okay, so when I have this thing right here, this width is actually a lot broader than that width, okay? So it turns out we also find out whenever they happen right around 30 MeV above the excited state, then this width is actually pretty broad. And that is because it's fit with optical phonon energy. So what that means is when you excite it, that this energy, if it's matched to the optical photon energy, it almost immediately decay to the exciton ground state. And since it decays so fast, so this is why the excited state lifetime is very short. And that lifetime, in fact, defines this width. But when you move far away, and then when you move away, then they become narrower and narrower. But if they are narrower than what the spectrometer can tell you, then it's kind of hard for you to know how narrow they are. So one of the things about quantum information, that is, we want to know, what is coherent time. So we ended up using this technique, the quantum interference, to measure the coherent time. And then we use this coherent time and then infer that it will be the optimal limit of the relaxation time. And then we find out, then we found this will be the T2 time that we get. So when they are matched this phonon energy range, they decay very fast. But when they move away from this optical phonon energy range, then the lifetime become longer, become measurable. But there is one region when you can find very, very long coherent time range, and that is when it's far away from the optical photon energy, but also not too close to be very low energy, because now what that means is in that energy range, you cannot emit optical phonon, but you can still emit acoustic phonon. But you need to emit a lot of acoustic phonon at the same time in order to relax, and the phase space for that is much more reduced. So that was really so once we find out where that is, then if you want to use this as a qubit and quantum coherent controller, then that would be the state you want to do. You want to use something with very, very large, very long coherent time. And typical coherent time we deal with is between 20 to 40 picosecond. And then our pulse width is about 5 picosecond. So you can see it's not that long. Of quality factor, it's not that long. But the whole thing changes once you can do the ground state excitation. So the coherent control of a two-level quantum system is usually defined with this Bloch equation, okay? And this is the Bloch vector, the dynamic of Bloch vector, and this is equal to this G is a gyration vector, and a cross product of that. And this is a little bit like what you do in your classical mechanics. You have a torque, okay? And how this torque behaves is also can be described by this equation. And in the external field, the gyration vector is really defined by your control. It's like your control pulse. And gyration vector can be written as this. This kappa is your dipole moment, okay? Yeah. And this E is the field strength. And the delta omega is the so-called detuning range. If you have delta omega equal to 0, just like the whole thing is exactly on resonance, then you will find this on resonance, then you'll find out then the whole dynamics become very, very simple. And then you can even solve this equation and find out the Z component of the Bloch vector has this kind of equation to govern it. And this solution is a very simple solution. It has minus cosine theta. And the probability is really the Z square, okay? So you will see this. And the angle, turns out, is equal to this thing called omega t if you have a steady and finite, just constant electric field. Then this thing omega is what we usually call the Rabi frequency. It's just the dipole moment times the field strength. And then this angle is just omega t. So if you think about in the Bloch sphere dynamics, okay, so Bloch sphere and cubic sphere this is in rotating frame. Now, in Bloch sphere dynamics, if I'm on resonance, what I would do is I'm tilting this Bloch spin, rotate it this way. Okay, so theta is equal to omega t, right? It's my Rabi frequency times the time. So I'm just rotating this. But of course, if you use a laser pulse, then its field strength is not constant. Then you will say, well, first slowly rotate, then it rotates fast, and then slow. Okay, so just remember that. But one thing you do know that is when you complete a pulse, then we'll just rotate. So if after one pulse is rotate the thing pi, then the state will then stay on top. If after complete one pulse, then the state, the angle is 2 pi, then the state recover to that state.